is something that, as we've been told, keeps track of open files. But this file descriptor information is kept for every process, because if a process opens a file or 2 files or 3 files, all the files that it has opened will have file descriptors. So that information will be kept in a file descriptor table. Now, each descriptor table keeps a file descriptor for the file opened by that application. I think I've already said that. So then, once the application has this file descriptor, then it uses that file descriptor to access the file. So remember that first and foremost, from the programs you've written, you first have to open the file. So you open the file and you get back a file descriptor. And then subsequent accesses to the file will use the file descriptor, not the name. So the only time you use the name of the file or the directory where the file is was when you open the file. Any subsequent access will be via the file descriptor. So the application then uses a file descriptor once it is returned by the operating system to access the file. And that file descriptor is basically an index into the file descriptor table. Remember that an application may have several files open at the same time, and they may be opened in different modes, some for reading, for writing, for reading and writing at the same time. But either way, that information is kept in a file descriptor table. Now, that file descriptor table contains a pointer to the details of that file. So the file descriptor is what an application uses to access the file, but the details of the file, remember the file has several other details. For example, like we said, what mode is it opening? Is it for reading? Is it for writing? That information is not in the file descriptor. So if you've opened a file for reading and then you choose to access it by writing to it, how will the operating system know that you're doing the right thing? It will refer to the that table that has the details. It's called a file table. So what is in the open file table? What is in the open file table is basically details about the open file. For example, the current offset. If you have read how far into the file you have read, it will have the access mode, as I've said, for reading or writing. Those details will be in the file table. And remember, the file table has a pointer from the file descriptor table to the file table. And of course, it has something also called an inode. I want to believe that whenever you did this, you also came across something called an inode. And an inode is now the one that gives you the actual details of the file. Some details that were not in the open file table, like the permissions on the file, the type of file that it is, and so on and so forth. So if you look at that last bullet, the inode of the table will give you the persistent attributes of a file, such as the type of file you're talking about, the permissions on that file, when it was last read, when it was last written. All those things are kept in the inode. So here we have 3 tables. We have the file descriptor table, which, as we said, just contains the file descriptor. And remember, the file descriptor is just an integer. 0, 1, 2, 3, 4. It's simply an integer. Then the file descriptor table points to the open file table. The open file table keeps details of the open file. As we've said, the current offset, how far you have read or written into the file, whether you're reading it or it's open for reading or for writing, those are the attributes that have to do with the file you have opened. Then there are the persistent attributes, the type of file, the permissions that are on that file, and so on. So there are 3 tables here I want you to be aware of that are kept. So this diagram here just tries to put what I've said in in pictorial form. The first table is called the file descriptor table, and we've said it contains a file descriptor, which is just an integer. So as you notice, there are several files there, 0, 1, 2, 3, they are just numbered by some integer. But now that file descriptor table has a pointer to the details of that open file. Did you open it for reading? Did you open it for writing? How far have you written? In other words, what's your offset? Are you still at the beginning of the file? Are you at the end of the file? Those details will be kept in the file table. And notice that the file table is global. Okay, it is for all files. Okay, then that file table has a pointer now to the persistent details of the file, like exactly where is it stored. And if it is not a file, maybe it's an input-output device. Okay, where are the details stored? Okay, so the inode table is where you have the persistent, the type of the file, the permissions allowed, and so on. So those tables are kept by the operating system. Now, of course, you're wondering, what has that got to do with system calls? Not with system calls, with the primitives you're talking about, the transport layer. I'll explain that in a short while. So as I mentioned, the file descriptor is a non-negative integer. It's just a positive integer. And the file descriptor is available for all types of files. In other words, in Unix, everything is a file. Everything to do with input-output uses the abstraction of a file. So even if it's disk, or it is the visual display unit, when you want to read or write to it, you write to it as though you are writing to a file, or as though you are reading from a file. So they all use the same abstraction of a file. Everything in Unix is a file that is of input-output. Okay, so file descriptors are used to refer to all types of open files. And these includes pipes, include fast in, fast output, data structures, sockets, terminals, devices, and regular files. Now, each process has its own set of descriptors. So the descriptors are per process. Every process has a table that shows the files it has opened. Now, as you said, you perform input output using descriptors rather than the name. And so all kinds of input output you can do. So there are just some examples of file operations: open, read, write, and close. Those are the operations that are provided for file operations. And remember, file can be anything. So here is an example of the tables that would be kept by an operating system. On my left-hand side are the per process file descriptors. So notice there's process 1 and process 2. And process 1 has several file descriptors. Process 2 has several file descriptors. Then there is the file table that contains the details for all the open files. And it's a system-wide table. So you notice, for example, that process 1 and process 2, there are some pointers that are pointing to the same file in the open file table. That means that process 1 and process 2 have opened the same file. That's what it means. Then from the open file table, then it now links to the inode, which has the persistent details of the files. In other words, where exactly is that file even stored on disk? Where would you find it? Okay, so I just wanted to bring in the idea of per process descriptors. Every process has its own file descriptors. And these file descriptors may map to the same file, even if they are different processes. And that's how the operating system finds the files wherever they are. This also is a diagram that just shows the same thing. There's process A and B, and they have opened several files. Some of them are mapping to the same file. And then the inode shows where the files are. Now, the other thing that this diagram shows is that every process has at least 3 default files open. One for input, one for output, and one for error. That's by default. So usually you have file descriptor 0, 1, and 2 already open for every process that is active. That's why your process can read and write to the visual display unit, because that is assumed that every process that is open will need to write to the visual display unit and to write and to read from it. And every error that it generates will also be sent to the visual display unit. And so those are 3 automatic files open. So this is where we begin with the primitives. Now, the TCP/IP was integrated into the operating system, the Unix operating system. Some people did that job. I think at one of the universities, they were asked to integrate TCP/IP into the operating system. So they decided to do that. Now, of course, Unix was already having this file concept that everything was referred to as a file. So when they integrated the TCP/IP into the operating system, and because it was supposed to be used for input and output, that is for communication with other computers, then they just integrated it into the file concept of the Unix operating system. So they decided to integrate TCP/IP into the operating system, and this was supposed to provide communication between applications. And notice that it was based on the already existing input-output paradigm, which is, as we said, is based on a file and is based on these operations: open, close, read, write, seek, and so on. So that means that the transport primitives would follow the same paradigm of using open, close, read, and write. So the socket abstraction was added to the input-output paradigm, which we have already described, to be able to perform network communication. And that interface was referred to as the socket interface. In other words, the operations that it provides form the interface, the TCP/IP interface. Now, so remember that they created something called a socket abstraction. And the socket was supposed to be the endpoints for communication. So if you have 2 applications communicating, they were going to use something called a socket. This abstraction called a socket. So as they were integrating TCP/IP into the operating system, they came up with this abstraction called a socket. And basically a socket is an endpoint for communication. That's really what it is. So if you have 2 programs communicating, the 2 ends of the communication channel is referred to as a socket. So on one side you have a socket, on the other side you have a socket. So it's like the endpoints for communication. So the server uses a socket and a client. If you have a client-server communication, then a client will use a socket and the server will also use a socket. Only that the server socket is passive. I think we've mentioned that several times. And the client socket is active, which means it initiates a connection. The server socket just sits there and waits for connection requests. So when an application creates a socket, they are allocated a socket descriptor or a file descriptor, only that this time it is referred to also as a socket descriptor. Remember, when you open a file, you get back a file descriptor. So if you open a socket, create a socket, you also get back a file descriptor. You can also call it a socket descriptor. So when an application creates a socket, the operating system allocates a socket data structure. Remember, I have just mentioned that for every file that is open, there is a data structure. In fact, there are 3 data structures, as we have just looked. For every file that is open, those are the data structures that are created for every file that is open. So you get back a file descriptor, and the operating system keeps some data structures. In this particular case, it will keep the file descriptor table that contains the file descriptor and the global file table. So the same thing happens when you open a socket. You get back a descriptor, plus the operating system creates a data structure, and we call this data structure a socket data structure. In the file case, you actually get a file table. You get a file table which contains the details of the file. Now, the pointer to the socket data structure is kept in the file descriptor table. So of course, you get a socket descriptor. That socket descriptor is kept in the file descriptor table, and then it has a pointer to another data structure, which we are calling here the socket data structure. And that socket data structure keeps details about that open connection. Remember, we had the open file table, which kept details about the open file. So in this case, the socket data structure keeps information about the open connection, the connection you have just opened. So this is how it would look like. On the left-hand side, we have the file descriptor table or the socket descriptor table. So it just contains a list of integers, because a socket descriptor or a file descriptor is simply an integer. So we have the file descriptor table with some integers, which is then returned to your application. But now this file descriptor table, socket descriptor table, has a pointer to another data structure, which here we are calling the socket data structure. Now notice the things that are in that socket data structure. There are things we have talked about, some of them I believe. We have talked about the local IP and the remote IP. Remember, we said that any connection is identified by 4 items: the local IP, the remote IP, the local port, and the remote port. So all those things are kept in the socket data structure. Now, of course, in this case, we have other things kept, like the service, whether you're using TCP or UDP, that is the service, and the family, whether you're using the internet family of protocols or whichever family you're using. Okay, so that is what the operating system does. So once you're given the file descriptor or the socket descriptor, any subsequent communication to send or receive data will be made via the descriptor. Now notice that in this data structure that I have just referred to, when you open this, when you open the socket, or when you create the socket, all these details are not there. This is a connection that all the details have been filled up. But initially, when you open the socket, some of the fields are empty, because you can just open a socket and you haven't said who you want to connect to. So the operating system won't know. So the fields might be empty. But at a later time, when that is specified, then the operating system will fill in those details. So that is one part that we have looked at. Let me just summarize for you what we have said. That TCP uses the same paradigm as you use in files. In other words, the way you do communication in Unix is the same way you would read and write files. So you would open a file, you would read and write to a file as many times as you want, and then you would close the file. So in the same manner, when you want to communicate, you would open something we call a socket. Then you would read and write to that socket, read from and write to that socket as many times as you want, and then you would close the socket. That is generally what I'm trying to say. So it was integrated into this file system. And it was supposed to work just the way the file system works. Now, this is point number 2. Now, the socket interface that was created, that socket abstraction that was created, is not specific to TCP/IP. Remember their job, this, I don't know whether there were students come staff that were given this job. Theirs was to integrate TCP/IP into the operating system. But they chose to make it more generic so that it will not apply only to TCP/IP. I believe they foresaw that maybe in future somebody may want to create another set of protocols, and so they wouldn't have to do or repeat the same thing again for that set of protocols. So they made it generic. So this socket abstraction is not specific to TCP/IP. If you have another set of protocols that you want to use, you can as well use sockets on it. But for our case, we will only be concerned with the TCP/IP, but just to know that it is not specific to TCP/IP. So when they made it generic, then they had to come up with a way of distinguishing the different protocols. So they came up with something referred to as a family of protocols. So every set of protocols will belong to a specific family. So in the case of TCP/IP, they would belong to the Internet family of protocols. So the family of protocols for TCP/IP is referred to there as PF_INET or Internet. So the protocol family of the Internet. I guess for any other protocol family, they would have to come up with another name. Then, once you specify the family of protocols, then you also have to specify the type. Remember that we've said that TCP/IP is a family of protocols. So there's TCP, there's IP, and of course, there's also UDP. So because you have UDP/IP also. When you're using UDP, you use UDP on top of IP. So you can have UDP/IP, TCP/IP. So when you have specified the family of protocols, then you also have to specify which type of service. Is it TCP or is it UDP? So notice there I've underlined stream and datagram. Stream is the one that refers to the TCP. And datagram is the one that refers to UDP. Now, I haven't said much about this stream, but I would like you to read a little bit more about it. But I will just say a few words about the stream service. The stream service, which is provided by TCP, assumes that when you write or read from a socket, you read data as a stream of bytes. That's, let me try and draw it. So assume this is your socket and you're reading, your application is reading data from that socket. It will read it as a stream of bytes. Now, data may have been sent as a series of bytes. Remember, we said when you're sending, the bytes are numbered. Each byte is numbered when it is being sent. So maybe that was the first packet. It ended there. Then another packet was sent, still on the same connection. So another stream of bytes was sent. Maybe it ended there, and another packet was sent or segment. As far as the application is concerned, this is just a stream of bytes. The only reason you broke it up into smaller bits is because they cannot fit in the data structure you are using to send. That's the only reason why it was broken down. But as far as this application here is concerned, it is one stream of bytes from here all the way. And that means, according to this application, it does not see these intermediate, I don't know whether to call them stages. It doesn't see. So for example, if this was 7 bytes, I don't know how many those are, but let's assume there are 9 bytes. I don't know whether that's 9. And maybe this was 6 bytes. And maybe this was 5 bytes. Now what the total is that? Total is 15 plus 5, 20. This application can decide to read 15 bytes all at a go. It can, he said once you open a file, you can read and write. It can decide to read 15 of them, 15 bytes, all at a go. Because according to it, this connection it has opened is for sending and receiving a huge stream of bytes. It doesn't matter how. So it will just depend on how much it can read at any time. Alternatively, it can decide to read 3 at a time. So maybe the first read will say, give me the first 3 bytes. The second read will give me the next 3 bytes, and so on. So you notice that if you are reading 3 bytes at a time, it will take you 3 read statements to read the first 9 bytes. Then it will take you 2 read statements to read these 2 bytes, these 6 bytes. Then of course you will read the first 3, and you will be given 3, and then there'll be 2 bytes left. Alternatively, you can read them in bytes of 6 bytes at a go. So what am I saying? The TCP/IP service is a stream service. Whatever is put in the channel when it is being sent is seen as a stream of bytes. How the application chooses to read the bytes is up to the application, at what pace it wants to read. Similarly, when it is sending data, assume it has data in a file which it wants to send. It sees that data as a stream of bytes which it wants to send. So again, it can decide to take them 3 bytes at a time, 10 bytes at a time. It can take 3 bytes, and then the next time it decides to send 5 bytes, and the next time it decides to send 15. There is no strictness about it, because it sees just the file as a stream of bytes which it needs to send. So if it chooses to divide them, how it chooses to divide them, how it chooses to read them is up to the application. Now, the datagram service is a little bit different, because each data sent is sent as a datagram. In other words, it's a complete data. And so if you want to read or if you want to send, you send one datagram at a time. And the reader will only read one datagram at a time. Of course, again, the datagram may contain variable data, but you must read a single datagram. In other words, if the sender sent one datagram, you will read that datagram, only that one datagram which was sent. Okay, so I hope you understand the difference between a stream service and a datagram service. But, so when you are using sockets, you have to say which type of service do you want, because that will determine how you use a socket. So you have to specify which of those services are you interested in. So anyway, as we've said, they created the transport socket abstraction, and the socket abstraction was used for sending and receiving data. And then they created this notion of families. To try and make it generic, you had to specify which family of protocols you are using, and within that family, which service exactly do you want. Now, this is another very important thing, that when you are sending data, as we've said, you must create a socket on both ends of your communication channel. So you have communication endpoints. Now, when we started talking about the transport layer and the mechanisms it provides, one of the first things we talked about was the address. Because really, it is applications trying to talk to each other. So how do you address an application that you want to talk to? And we said that each of those endpoints has a composite address. So there must be a way to address that endpoint. And the way you address that endpoint depends on the family of protocols you're using. Now, because we said we are not using another family, we are using TCP and IP. So now we come back to TCP and IP. How do they address that endpoint? We said they address it using the IP address and the protocol port number. Or IP address, port, that is the composite address. Now notice it is specific to a given family of protocols. So the communication endpoint is defined by the address family. In the case of IP, it is defined by IP and port. So that really means this, that when you are creating that socket, as we said, you have to say which family of protocols you're interested in. Is it IP? Is it TCP/IP, or is it another one? And so you also have to specify the address family, because every protocol family has their own address structure, which here is referred to as an address family. So you have to specify that address family. Just 1 minute. Okay, so for the internet family of protocols, the address family is referred to by that acronym AF_INET. So therefore, when you are creating the socket, you must specify that the addresses you are using come from this internet family of addresses. And that will just provide an understanding of what type of endpoint address you are using, because every family of protocols uses a different type of endpoint address. So it will obviously, when you say address family _internet, they will know the type of address you'll be using is the IP address, port number, the composite address we talked about. So that too has to be specified. And the reason for all this is because the socket structure is a generic abstraction that can be used with any family of protocols. Now, following from that, there is a predefined structure declaration for each protocol family. In other words, when this TCP/IP was integrated into the operating system, they predefined a structure that would be used to contain the address for each and every family of protocols. It's a predefined structure. So that means this: if you want to specify the endpoint that you want to communicate with, you must define it according to this structure. You must take that address and put it in this predefined structure. That's just what it means. Now, the structure represents a family's representation of the endpoint address. I think I've already said that. Now, for the TCP/IP, the predefined structure, which is referred to as SOC address underscore in, it provides the following fields. In other words, this is the way you would define an address. If you're using TCP, you'd have to define the address family. Now, remember we said the address family is AF underscore INET. So you're not putting there the protocol family, you're putting the address family. Then you put the protocol number or the port number, and then you put the IP address in this predefined structure. So now, assume you have understood that concept of families and doing things according to the family that you've chosen, and that there is a predefined structure that you must use, and the format of that predefined structure. I just want you to look at this structure, because this is the predefined structure that you must use, and you must become familiar with it. And this structure is supposed to contain the address according to the way that family of addresses is supposed to be. Now, if you look at the lower structure, which we said is SOC address underscore in, notice the fields that it has. It has one which is referred to as the length, SYN underscore length, which is the length of the structure. Then there is SYN underscore family, and in that variable, you would put the family, the address family. So if you look at the comments there, you notice that the address family that would be put there would be AF underscore INET. Then there is SYN underscore port, and in that variable, you'd put the port number. And remember, it is 16-bit port number. So obviously, you would put there a value that is not greater than 16 bits, the numbers that would be stored in a 16-bit field. And notice there's something there very important, that it is in network byte order. The value you put there must be network byte order. Why is that important? It is important because the two sides that are communicating are on different machines. And of course, with networking, we say that they must come to an agreement in their communication in terms of how they communicate, so that they can understand each other. So what is being said here is that when you want to connect to a different client or a different application, the address you specify must be in a specific format. And that format, when it is communicated to this other machine, there will be no confusion about what exactly you are talking about. So it will be put in a standardized format. This standardized format is referred to as a network byte order. Now, I want to leave it to you as an exercise between today and the next class we have to find out what network byte order really means. But all I'm trying to say is that it is a standard format for communicating addresses, both the port number and the IP address must be communicated in network byte order. So we have looked at the SYN underscore port, and then there's the SYN underscore address, and that's where you put the IP address. Now notice that that variable is in itself a struct. So here we have a struct within a struct, and if you look at the top, that struct in underscore address has been defined on top. And it contains a variable called S underscore address. So you just have to remember that this is a struct within a struct. So how you refer to it will be important. You'll have to put SYN address dot in address dot S address, something like that, because it's a struct within a struct. And then notice that the other, this one is unused. This is unused. Secondly, I had not talked about this, but there is a part that gives you the length of the structure. Now, let me show it in diagrammatic form. So we have said that that structure for address contains a length of the structure. It contains the family of addresses, and then it contains the actual composite address. So this is the composite address, which in the case of TCP contains both the port and the IP. So notice that first you must declare the length of the structure and the length of the structure and the family address. Okay. Now this diagram is a little bit expanded. Notice here that the length is 2 bytes and the family is 2 bytes. And the rest is a number of bytes. Here it is not described. Now, if we look at the generic structure that was declared, that was created by those who are trying to integrate this thing into the operating system, they had a generic structure, which here it is written as family, but from the upper diagram, we notice that 2 bytes must contain the length, and the other 2 bytes must contain no, it doesn't here. Wait a minute. Yeah, sorry, no, this is the 2 bytes for the family, but the assumption here is that there is something called length, which is also 2 bytes. The length would be there. So here it's just talking about the family having 2 bytes. And then notice that there are 14 bytes. In other words, this variable here is 14 bytes. That's what it means. Now, if you look at it in the IP case, because this is the generic structure that will be used by all families. In the case of IP, of course, you would have the family, which would be AF INET. Then you would have 2 bytes or 16 bits for the port number. Then you would have 4 bytes for the IPv4, 4 bytes for the IP address. Now, in a case where you have 16 bytes, you will be left with another 8 bytes unused, because this would then be 4 plus 2 plus 2, which is 8 bytes. So the remaining 8 bytes of these 14 bytes here, or 16 bytes, is unused in the case of the TCP/IP. Of course, it was generic, so they didn't know what the other family of protocols would use, what kind of endpoint addresses they would use, how many bytes they would need. So that's why it was left open with 14 bytes. And it could obviously be used by other protocols depending on how they see it fit. But for IP, this is the way it would use that generic structure. Which structure are we talking about? SOC address in this one, this structure here, this one. And so we've said that there would be 2 bytes for the family, 2 bytes for the port number, and 4 bytes for the IP address. Then this length here, I believe, is also for 2 bytes. The length of the structure is also 2 bytes. Okay, so that means that if we are using that structure, as I think I've already explained this, maybe this is just in words. The scene.family will contain the family, scene.port will contain the port value, scene address.s address field, because we said it's a structure within a structure, would contain the internet address, also in network byte order. And then the scene0 would be the unused part of it. Now, there's something there called in address underscore any. In other words, in the part where you're supposed to put an address, the IP address of the machine where that particular application is, you can either put a very specific address, or you may put in this variable here, in address underscore any, to refer to any of the IP addresses of that machine. Meaning that if that machine has several IP addresses, as we saw last time when we were talking about the number of connections, we said it depends on how many IP addresses are on that machine. So if you want all the IP addresses to be used in that connection, then you use this in address underscore any. You put that in the IP address part. However, if you have a very specific address you want to use, then you would put that specific address in the scene address.s address field. So the choice would be up to you. And when you use this in address underscore any, it would mean it can accept a connection using any one of those IP addresses. That's really what it means. Okay, so this is an example of what you would have in your program. Having said all that, so now if you were to write a program based on what we have talked about, this is how your program would look like. And this is only for the description of the data structure. Okay? So notice that the first statement there is struct, because it is a predefined structure, and it is referred to as SOC address underscore in. So it's a structure of that type, or a record of that type. And then you give it a variable name. In this case, in your program, you've chosen to give it server. So maybe you are trying to create an address for a server you want to connect to. So you give this variable, this structure type, a variable name called server. And then you put the address in that predefined structure. So notice that in the server.scene family field, you put the AF underscore INET, which means it belongs to the internet family of address. Then in the server.scene underscore port, you put port 80. And now this function, HTONS, is the function that converts that 80 into what we called the network byte order. So you wouldn't just say server.scene port equals 80. No, you must make sure you convert it into the network byte order. And these functions are also available. So all you need to do is to make sure you include the file where these functions are defined. Then in the address part, you would use server.syn_address dot, because it was a structure inside another structure, .s_address, and then you give the IP address. And again, this function here converts it into network byte order. So I asked you to read about this network byte order, but please note that the functions for doing that are available. You just need to know which function to use to convert it to network byte order. And now this structure is ready for using. So if you want to connect, then you would say use connect, and you would put this structure, which you have named server. You would put it inside the connect function to say, look, I want to connect to this server. The server with port number this and address number this. And that these addresses belong to the internet family of address. That's really what you would be saying. So first and foremost, you must construct the address that you want to use according to the rules provided there. And that brings me to the first part of the this section. So any questions? Because now we'll be very specific in terms of those primitives: connect, send, receive, and so on. Any questions? Yes, go ahead.
Yes, there's the section which is called syn0. I suppose that's the extra padding for the
Yes.
package. And
Yeah.
can someone change it? Like maybe you don't put zeros, you put something else. Is that allowed?
I'm not sure what effect that would be. I don't know what effect it would have, because remember, we have already said that this predefined structure was meant to take care of all the different families. So now, if the receiver is expecting an address from the family of addresses on the internet, which we said is a mixture of the port number, which is 2 bytes, and the IP address, which is 4 bytes, then you go ahead and add other things at the end. I'm not sure what effect it will have, because you are really violating the address structure of the TCP/IP. So I guess you could put, but I can't promise you I know what effect it will have, because you'd be in violation. But maybe you would want to try and see what happens. But as shown there in the structure, it should really be 0. It should have zeros, which basically means there is no address there. I think it says you should have zeros, right? So
Yes.
that would be my answer. Of course, there's nothing to stop you putting there what you want, but I think you'd be in violation. Yeah, I think it says you should put 0, is it?
Yes,
It's
it says
unused, but
padding zeros.
I think there's somewhere where we said it should really be zeros. It should really have zeros. Yeah, you should zero it ideally to avoid that confusion. Yeah, I think here it was said it must be set to all zeros. Whatever else you set it to, maybe it may work, I don't know, but it will be in violation. Okay. So now we talk about these primitives. And remember I said these are all the primitives you need to program your communication part of the program. This is all you need to know. Of course, not all. Of course, I've already shown you that predefined structure. I've already talked about the network byte order. So there are a few other functions you may need, but these are the key ones, right? These are the key ones for communication. So this is for BSD sockets, remember. As I said, there may be another family, but we are going to use this one. Now, notice that these things were added to Unix, and of course now to many other operating systems along the Unix line. Now, obviously, they were packaged as a library of functions, and so you can call them. Now, at the application level, they would put a wrapper around these functions. Remember, these are the functions that you call when you are making system calls into the operating system. But from the language level, they would give you another library on top of this. And so most of the languages that are built on top of Unix will give you some kind of socket that has these primitives in some form or another. So they will provide something similar, but we are going to look at it as in how it is defined as a system call into the operating system. Now, this part we had already done in terms of, in fact, let me do it in diagrammatic form. We already talked about the ones used on the client side and the ones used on the server side and the order in which they are used. So you need to look at that order because it's important. And then for the connectionless, this is for the connection oriented, where you connect and you do the three-way handshaking and so on. For the connectionless, remember for the connectionless, remember you don't create a connection. And remember we said that when you don't create a connection, you're not even aware whether the other side is there. You may send data and the application you're sending to, it does not even exist. So basically you don't create a connection. So you would leave out the part for connect. So if we look at the server side, notice that server creates a socket, binds an address to it because that's what bind does, and then is ready to receive from any client. The client does not have to connect to the server. So it will receive data from different clients that had not made any prior arrangement to connect to it. So it will use receive from, and then of course it will try to understand what the client is trying to say. Then it will get a response, whatever that response means. Maybe the client is asking for a file, I don't know. Maybe the client is asking it to add 2 + 2, we don't know. But whatever the client asks, once it has received, it will try to understand it and try to respond to it. And once it has a response, then it will use the send to respond, to send back a reply to the client. And notice that this receive from, if there is nothing to receive, then it will block. The application will block. And that is the same even for this other one. If an application says issues a command to receive and there's nothing yet to receive, the operating system will block it until some data comes in. So that is always the case. But all I wanted to say about the connectionless, there is no need to connect at all. And so we'll talk about how then do they communicate. Now, this other diagram, I want you to see that we are using a connect, but that's a very specific case. And that is a case where a client is binding themselves to only talk to a given server, a very specific server. For whatever reason, if they want to do that, they're allowed. But notice that in this first diagram, the client doesn't say which server they are going to talk to. So which means they can send that data to many servers if they wish. They are not bound to one server. But in this particular case, a server decides to bind themselves to one server. For whatever reason, may be necessary, but you can use connect in that case. So anyway, so let's let's take these primitives one by one. Now we are on the server side. Then we will go to the client side. So if you want to keep an eye on these diagrams, it may help, but we are on the server side in each case. Now, as we have said, the first thing that an application must do is to create a socket. So when you start writing your programs, make sure if that program wants to communicate, it must create a socket. So how do you create a socket? You create a socket using the socket primitive. Notice that this primitive creates a new communication endpoint and allocates table space. Now, I've already shown you the tables which will be created when a socket is created. A table that will contain the details of that connection. Now, what is the format? The format is as shown there. Notice that we have the keyword socket, and in brackets we have 3 arguments. One is the domain, one is the type, and one is the protocol. And notice that the return type is an integer. So if you look at the arguments and what is included in the argument, we'll go through each of those arguments in turn. The domain specifies the address family, as I already explained. So in there, you would put AF_INET, and that is only for IPv4. I believe for IPv6, they have another name there. The type of service, we said you can either choose TCP, which is the stream service, or you may choose the UDP, which is the datagram service. So if you're choosing the stream service, you would put in there sock_stream. If you're using the datagram service, in that argument, you will put sock_dgram. And then the third argument there is the protocol, because we said once you choose the service, you have to say which protocol exactly, because there could be many stream type of protocols. There could be many datagram types of protocol. So you have to say which one. But if you put 0, you're choosing the default. So in this case, if you choose the stream service and in the protocol you put 0, it means you're choosing TCP, because it is the default stream service for TCP/IP. If you choose the sock_dgram and in the protocol field you put 0, by default you're choosing UDP. So anyway, that is the way you would put that instruction in your program, and make sure you specify everything as written. And notice you must prepare to receive a return type of integer type. So you'll have to create an integer variable to receive the return value. So here is an example, something you would have in your program. Notice we've declared an integer called socket_descriptor. It really stands for the descriptor, because remember we said when you create a socket, you get back a descriptor, a file descriptor for that socket. And that is the integer that you should be ready to receive back. So you put socket descriptor_descriptor is equal to, then now that statement creates a socket. So you say which type of socket you want to create of the address family, for that socket, the type of service, which is sock_stream_stream. And then, as we said, if you put 0 there, you are talking about the default, which in this case means TCP. So that's what you would have in your diagram, in your program to create a socket. And what is the return value of socket? Notice a successful socket call returns an ordinary file descriptor, which is a non-negative integer. So obviously, if you want to know whether the socket was created, you have to test whether the return value is a non-negative integer. Else, if the socket was not created, then what you would receive would be a -1. If there was an error, in creating the socket, maybe you didn't define things correctly, then whatever the reason, you will get a negative number. So whenever you create a socket, you must make a point of checking whether that socket descriptor contains a non-negative number or whether it contains -1 to mean actually the socket was not even created. So that's for the socket. Bind. And this is on the server side because the server must bind itself to a well-known address, depending on which server type it is. So if the server wants to say this is the address from which I will be receiving data, then it has to use this bind statement. So notice that a new socket, like the one we just created in the previous slide, does not have any address. So to give it an address, you use the bind primitive. And this is used on this socket on the server side to assign a composite address. Okay. So this address specifies the address at which the server will be willing to wait. Look at the format. And now this format, you must remember the data structure we talked about. Sock address underscore in. And I think here it needs to be identified as such. Now, so notice the format. The return type, of course, is an int. But after the bind, there are several arguments there. The first argument is the socket descriptor. Remember, we said after you opened a socket, anytime you use the socket subsequently, you use its socket descriptor. In this case, the one that was returned here, this socket descriptor that was returned, that is the one now you will use to refer to that socket. So the first argument there is the socket FD is a socket descriptor. Then notice that the second argument is that sock address in. And the variable name or the pointer that is pointing to that socket address structure, predefined structure, has been given a name, my address. In other words, that's the address that the socket wants to use. The third argument is the socket length. That is the length of that address. So there are 3 arguments. So that's the format of bind. You put in 3 arguments and you get back an integer value. Now the arguments are defined here. I've already mentioned them though. The arguments includes the sock FD is the socket descriptor. The my address, notice it's a pointer. It's a pointer to the sock address structure, that predefined structure. And it contains the address which you want to bind to, which the server wants to bind to. Address length is a field of type socket length. Again, this socket length underscore T is predefined. It is actually a predefined variable. So notice here, address length or address len is of type socket len underscore T. So that type is also predefined. Okay? But it specifies the size of the address structure in bytes. So I guess the question that was being asked by I think it was Craig, if you put other values in that space that was supposed to be unused, then I don't know what your address length will be, because it will basically try to find out how long that address is. Now, if it returns an address that is greater than 16 bytes, I am not sure what will happen. But just notice that the type is predefined, and in there you specify the address of the length of your address. Now, the return value. If the bind is successful, the return value is 0. If it is unsuccessful, the return value is -1. And again, whenever you use these primitives, please check the return value so that you know whether it was successful or not successful. So here is an example of something you would have in your program to use bind, for example. Notice that the first statement there creates that predefined structure for putting the address. So it's a struct of type, it's a struct of type sock address underscore in. The variable name is server. Assume it's the server that, usually it's the server that wants to bind. Then you create the socket. So the second statement there creates the socket. And it gets a return value of type integer. Of course, that means we should have created the sock descriptor as an integer variable. So that's missing in your program, but I guess you know from the previous case that this socket underscore descriptor should have been defined as an integer. Then now, since you've created this server of type sock address, you have to put in the address. So notice server.scene underscore family is AFINet. Server.scene address.scene address. I don't know whether that has been, yeah. So because it's a structure within a structure, you put in the address, and notice it puts in the in address underscore any. In other words, the server would be saying, I can receive connections from through any of the IP addresses on this machine. Okay? So it might be using port 80, but a connection may come through any one of the IP addresses on that machine. Then there is the port number. Here it uses port number 8888. But of course, if you are creating a server of a web server, you'd put there 80. But you can put any number. So here we are using 8888. And again, it's being converted to the network byte order. So now that structure server contains an appropriate address that the server can bind to. So now after that, you use the bind command. And as we say, the bind must have 3 variables. So notice it has the socket descriptor as the first variable. The second variable, it's a pointer to this sock address. And so, I mean, I guess you just have to know C to understand this. So the ampersand server there provides a pointer, obviously. Then there is the size of server. So this size of function is the one that will look into that structure to find out what is the size of your address. How many bytes is it? So it's just a function you call, and it will provide the number of bytes in that structure that you've just created. Right, so that is for bind. And I don't know if there are any questions, but you can always go back and reread this and use those examples in your slides to create programs, depending on what you're doing. Those are just examples, but they're examples you can use in your program. Then now there's the listen command. And we say the listen command is the one that the server uses to say that it is willing to accept connections and how many pending connections it can accept, or how many connections can be pending in the queue. So the listen primitive puts a bound socket in passive mode, because the minute it says that it is willing to receive, then it will go into the passive mode where it will just wait. It will just wait for those connections to come in. So it's, in a way, it's putting it in the passive mode and also allocating space for those connections when they come in. So it will specify the size of that queue so that it can accommodate a number of client connection calls. Now, listen is not a blocking call. In other words, the server will not block. It will not be blocked. When it calls that listen call, there will be no blockage whatsoever. So what's the format of the listen? Again, notice that the return type is an integer and it has two arguments. The first one is the socket descriptor. So you always have to say which socket you're using, and you say that using the socket descriptor. And then the only thing it specifies there is the size of the queue. Here it's written as backlog, but it really means the size of the queue. So it's just a value, like 3, 4, 5, how many connection calls can be in that queue, or what's the size of the queue. So the arguments, of course, sock FD is the socket descriptor and backlog is an integer representing the number of pending connections that can be queued up at any one time. And notice that the operating system puts a limit, so you need to find out what is the limit that your operating system puts on that value. Now, an example here. Notice the listen statement simply has a socket descriptor and the value 3. You can make it 10 as long as it does not exceed the limit. So it's just a value, an integer value. Now, if successful, it will return 0. If unsuccessful, it will return -1. So always you need to check whether it was successful or not successful. Now, this one is a big one. This one is a big one, and it requires some understanding. Now, if I lose you at any point, please let me know. So remember, the server has created a socket. The server has bound an address to that socket, and the server has issued a listen command, which basically says, okay, I have told you my address. I am now waiting for any connections addressed to me. And I'm willing to have a queue of size, such and such. So now the server sits and waits, or should sit and wait. But how does the server know if a connection call has come? So it will have to use this command accept. So accept would be the statement it uses to say, I'm willing to accept any connection calls that have come in. So the accept primitive is used on the server side to accept an incoming connection request from the client. Now notice, if no request has been received, then the call blocks. In other words, that application will be blocked. That means it cannot proceed to the next statement until that call returns. Now, this part is the one, this second part or this second bullet is the one I'm saying it's a big one because you need to understand it. So let's assume a client has issued a request to connect to a server, and the server has also issued the accept call. So when it issues the accept call, the operating system says, okay, there's a client here wishing to accept, wishing to connect to you. So the call will return. But notice that when it returns having created another socket, a new socket. We are on the server side. Remember, the server had created a socket, and then it has issued an accept command. And that accept command, if there's a request, it will return with the request, but it will also return with a new socket. And that new socket is associated with the same address as the original socket. And it also returns what? The file descriptor of the new socket. I have put in that question just to remind you to think again. So what is the address of the new socket? Because we are saying a new socket is created. What is the address of that socket? And I think I have given you the answer to that question. Now, look at this diagram because it explains it in diagrammatic form what is happening here. So this is the server. The server has issued an accept command. So it has said, I'm willing to accept. It has gone through the other stages. Remember, it has created a socket, it has bound an address to it. It has issued the listen command saying how long the queue, how big the queue can be, and now it has issued an accept. Now, when the accept returns, if this call is successful and the accept returns, then it returns having created another socket. So this second diagram shows what really happens. So when it issued the command, it was only one socket. When the accept command finished, it had two sockets because it had created another one. It didn't create, the operating system created another socket. And if you remember what we said, how a socket looks like, it's a data structure. It's that data structure we talked about. So if that data structure is there, it means there's another socket. Right. So it has created another socket. Which was the original socket? This one. Which is the new socket? This one. Now notice, it is the new socket that is connected to the client. Because we are trying to create connections. So it is the new socket that is used to connect to that client. What is the purpose of this old socket? To accept new connections. That is the job of this original one. It accepts new connections. Connection requests, that is. But when it returns, it creates a connection using the new socket to the client that is requesting for a connection. And this old socket here goes back to listening. Remember, it was listening and waiting for connections. So this one goes back to listen. Okay. So that's how the accept behaves. So assume there's a server here. Let me just try to draw it. There's a server there. And there are hundreds of clients trying to connect to it. So many clients are trying to connect to it. When this one issues a connect request, the server will create a new socket. Then that new socket will be connected to this client. And now this client can talk to this socket, not to this one. It will now talk to this socket. When this one wants to create a connection, it sends a request to this server here. And then this server creates a new socket. And now this new socket will be connected to this client. And now the client will be talking to this socket and not the first one. Now, when this client wants to create a connection, it talks to this socket here. And this socket creates a new socket. And now this client will be connected to this socket and it will connect, it will be talking to this socket here. That is what is happening. When you use the accept command, there will always be a new socket created. When the server accepts any new connection request, it must create a new socket that will talk to that client. And then it goes back to listen. Because remember, the listen command was done by this server here. And in our case, it said it can wait for 3. It can accept 3 waiting connection calls. So any connections will always come here. They will always come here. They will always come into this queue. And then when the server removes one connection request, Using the accept call, it creates a new socket and connects to that client. It creates a new socket for every connection it removes from that queue. It creates a new socket. Now, on this socket, a duplicate of the server will be created. Remember that there's a server program running here. When it creates this socket, it must duplicate itself to have another program just like itself talking to the client. And then it will also create another program just like itself, a duplicate of itself, to talk to the client. So the client really doesn't see a difference because it's talking to a duplicate of the server. That duplicate is doing exactly what this server would have done. This one. It's just the same statements. So every time a new socket is created, the server duplicates itself and then tells the duplicate to continue talking to the client, and so on and so forth. So you need to understand that process when you start writing your program. So we've talked about the second part. So the third part there says the server can then fork off a process, that is the duplicate. Fork, as you know from what you've done, I hope you know. If you've used the fork system call, if you haven't, you need to go and find out what it does. But using the fork system call, the server can duplicate itself. Or it may pass off the new socket to a thread. It may create a new thread and let that thread continue talking to the client. So these new processes or new threads that are being created, they are supposed to handle the connection to the client that was asking for a connection. And then the original socket, notice the original socket goes back to waiting for the next connection request. I think I've explained it diagrammatically. I hope it makes sense. So now let's talk about the argument. And I think my time is slowly disappearing. The format of accept. Notice that the accept has several arguments and returns an integer. What are the arguments? The first argument, if you look at the argument, the first argument is always the socket descriptor. You must say which socket you're using. So the first argument is the socket descriptor. The second argument is that structure that contains an address or should contain an address. And the third argument is the address length. Now notice that here there's a client trying to make a connection. So there's a client here trying to make a connection. The client had created that SOC address in and said, I want to talk to server with IP address X and port number Y. It had already put that in the connect request. And then it sends that information to the other side, to the server. So the server gets the connection request from its queue. The server gets the connection request from its queue and then creates a socket, a new socket. But remember that in the accept command, when this server issued the accept, it must issue the accept to get a request from this queue. So the accept is always referring to this queue here. And that accept has this argument. So it has put the SOC descriptor, it has put that data structure that had family, it had length, and it had port, and it had address. So it has put a copy, a variable of that type, and then the address length, which is the size of that data structure. Now, when the server is doing that, it doesn't know which client is going to connect to it. It doesn't know. So the reason it's putting this data structure is so that the operating system can fill that data structure with information about which client is actually wanting to talk to it. because it doesn't know which clients want to talk to it. It is the operating system that is receiving these calls, or the transport layer that is receiving these calls, that gives the information to the operating system about which client is this that is trying to connect. In other words, what is the port number? What is the port number of this client that is trying to communicate? So when this call accept returns, this data structure, which was initially empty, will have been filled with some data by the operating system itself, or by the transport layer, I think. So now the server can look into this data structure to know which client is actually this client that is asking for a connection. Which client is it? So notice that the second argument is a pointer to a SOC address data structure, and address length is a pointer to an integer that contains the size of the structure pointed to by address. Now on return, address will contain the socket address of the connecting client, as I've just explained. It will be filled in there by the operating system. And the address length will contain a pointer to an integer that contains the size of that address, the size of the address of the client. So basically, that's how the server gets to know which client wants to talk to it. It looks in that data structure. So on the server side, when it creates that data structure, it will leave it empty. It will put it in the accept call, it will be empty, but when it returns, because it has a pointer to that data structure, it will find that this data structure has already been filled. And notice that the server will respond back to the client. So it will get that address from there to respond back to the client, because it already has the address of the client. So let me just finish. I know time is just about over. So let me finish here with an example. Here is an example. If you look at the first statement, we've created an integer type, which is a socket descriptor. That is for the initial socket. And then another variable there called new socket, which is for the new socket that will be created. And then the server creates a socket. As we already explained, it contains those variables. The socket function or command returns a socket descriptor for the original socket. That is the server's original socket. Now, then the server creates this data structure, the SOC address in. Notice that it creates two variables of that type, one called server and one called client. So there are two variables of type SOC address in. Then it finds out what is the size of that structure using the size of function. So size of that data structure will be returned as the number of bytes. Then notice it now issues the accept call. Of course, we have skipped there the bind. Remember, we have skipped the bind, and the bind would have used the server version of the struct. We have skipped there the bind. You can just pull it from the other slide and put it in there. But after bind, there would have been listen, and then now the next statement would have been accept. So now accept is in there. Now accept puts in the socket descriptor of the original socket. And then it puts the structure for the client. Notice there were two data structures, one for the server, one for the client. The server one was used to bind. The server one was used to bind, but now this one is used for accept. Why? So that it can receive the address of the client which is trying to connect to it. And again, it will receive the number of bytes in that data structure. And then it will receive the file descriptor for that new socket in the new socket variable. So after the accept, there will be socket, the original, there'll be the new socket. The socket descriptor for this one will be new. This will be the socket descriptor. So that copy of the of the server which will be dealing with this socket will now use this socket descriptor. The copy of the original server which will be dealing with this socket will use the old descriptor, the one called the socket descriptor. It will be using this socket descriptor. And I think there's something put in here that I don't know whether it's here or it was in another statement, where it says this new socket, this new program here cannot issue an accept call. Okay? This one cannot accept because it is not the original server. So it doesn't have any queue by which it can say, I want to accept connection calls on this socket. No, this socket here is not for accepting connections. It is for talking back to the server, to the client. So the client will say, will make a request through its socket. Whatever request the client makes will come to this socket here. This server here will respond to that request of the client. This one will only be for accepting connection calls. So all the communication that client and server will be doing will be here on this connection here. And this server cannot issue an accept on this socket. So please take note of that. Now, again, the return value, if successful, it will return a socket descriptor for the new socket. So it will be non-negative. If unsuccessful, it will return a -1, which means that accept was not successful. The new socket was not created. And then you can find out which error it was by looking into that error variable. And this is what I was referring to. The new socket descriptor cannot be used for new connections. And that brings me to the end of that, of the server side. I would have wished to have more time to do that, but I've run out of time, so we'll stop there. But I think we will finish that in our next class. Any questions? Yes, Roman. Mm-hmm. Exactly. It is the same port number. Remember, the client is not confused. The client created a connection and gave the address of the server it wanted to talk to. The client does not go back to create another connection. As far as the client is concerned, that's the server he's talking to. The only thing he doesn't know that he's talking to a copy of the server. So as far as the client is concerned, the address is still the same. The address has not changed. And you have to remember the things that we talked about. Remember, we said there's something called a file descriptor. There's something called a file descriptor table. So the original server was given a file descriptor. Let's just call maybe the file descriptor was 7. That was given to the original process. Now, when this process forks a new one, it is given a new file descriptor for which it will hand over. It will have to officially hand it over to this copy of the server. So this is the original server with a file descriptor, this one here. This is the new copy of the server with a file descriptor. And let's assume this file descriptor is 9. Okay? Now we said that these things point to another table which contains the details, the socket data structure. So if they point to the same data structure, then it's just the same socket. Do you see that? Yeah, it's just the same socket. Any other questions? Right. Our cut is on Friday. Is that okay? Oh, you want us to finish this before that?
Yes. Yes, I would like us to finish the whole topic first.
So that means our cut will be on Monday.
Yes,
Because
Monday is better.
Monday is better.
Okay.
Yeah.
Okay, no problem. So Friday, we will talk about the remaining part of the client and basically just get the idea of how to start programming. But please look at those reading assignments.
Okay.
Maybe I will communicate what you should look at for our Friday class. But I want you to understand what is the client server concept. Okay? All right, so we end there. I think you can begin to write your programs. Begin to write these programs. What you must do is make sure you include the right files, because you've seen so many functions here that are predefined. In your include files, make sure you include the right files. So it's time to start programming. At least make sure you can program the server. Make sure the server can, do all those things, and then wait for a request. If you can look at those functions in the client side and maybe try them, that would be good enough. Right, we'll stop there. We'll see you next time.